So good afternoon. I want to apologize first for the old coffee and the absence of cookies. I was told that because of the cancel week, well, we could not have a normal coffee break. So I'm glad to present you the speaker today, George Zweig, who actually had to give a seminar at CERN 50 years ago, in 1963, when he proposed the quark model before Gell-Mann while he was here. George was a student of Feynman, so he did his PhD in Caltech. And then he came to CERN for almost 1 year, from 1963 to 1964, where he wrote 2 preprints, which exist in the database of CERN on the quark model, which he called ACES. I guess he will speak about this. And then he went back to Caltech for several years, until 1987, as an assistant, associate, and full professor. In the meantime, he switched to a different field, to neurobiology, where he's an expert on the on the ear. In 1981, he went to Los Alamos National Lab for until 2000, and then since then he's in MIT. So today he's going to talk us on the quark model.
Well, this year is the 50th anniversary of the discovery of quarks. It's also at least last year was the 40th anniversary of the invention of QCD. Now, QCD developed in 2 phases. First, the discovery of quarks, and then the specification of their interactions. And work in these 2 areas really arose from 2 very different traditions, that of Rutherford and Bohr, and that of Einstein. The story really begins with Henri Becquerel's discovery of radioactivity. A few months after X-rays were discovered, Becquerel, who was interested in phosphorescence, was wondering if he could take salts of uranium and expose them to sunlight and then have them emit X-rays and take photographs with them. And much to his surprise, he found that he could get these uranium salts to emit something that he could take photographs with. And an example of one of his photographs is shown over here, where you can see a Maltese cross. Now, he didn't know what it was that was being emitted, and 3 years later, Rutherford at Cambridge found that there were 2 very different kinds of objects being emitted, which he called alpha and beta. And they were distinguished by their penetration power. Rutherford then in McGill University, with a young student called Sadi, worked out what was called the disintegration theory of radioactivity. That is, they showed that it was an atomic and not a molecular process. Rutherford received the Nobel Prize in Chemistry in 1908 for this work, and Sadi received another Nobel Prize in Chemistry for entirely different work in 1921. In fact, it's rather remarkable that there were 11 Nobel Prize winners associated with Rutherford. This was either his students or his postdocs or people that were working in his laboratory. Now, you see here a picture of Rutherford, and this is a couple of years after he got the prize at Manchester University with his group. Now, things really got interesting when a postdoc came to work with him, Hans Geiger from Germany. And Geiger worked with a young student, he was only 20 years old at the time, Marsden. And together they published this very interesting paper in the Proceedings of the Royal Society. And let me just read from a part of the paper. It says, in the following experiments, conclusive evidence was found of the existence of a diffuse reflection of the alpha particles. Let me just say that they were taking alpha particles and sending them towards a metal foil and then looking at the scattering. Very modern experiment, scattering experiment. They say here, a small fraction of the alpha particles falling upon a metal plate have their directions changed to such an extent that they merge again at the side of incidence. This was a very unexpected answer because they thought that the atom was some diffuse object and it couldn't possibly give you these large backscatters. And 2 years later, Rutherford in 1911 published his interpretation of this experiment, where he said that the charges in the atom are actually separated. They had to be pulled apart, and you were getting scattering off of some object in the center, the nucleus. So he discovered the nucleus. Now, this idea that you separated the charge was really impossible according to classical theory, because either the charges were static, in which case they would fall together, or one was moving around the other, and in that case you'd get Bremsstrahlung radiation and you get the two objects to spiral together anyways. So keeping them separated was really impossible. And the problem even got more peculiar in 1914 when Marsden went on to show that the nuclei actually contain protons. So here you have this nucleus, and it's got all these positively charged particles in it. It should explode. Bohr, right after he got his thesis, and he was working on electrons and metals, wanted to go where the action was, where they knew about electrons, which was J.J. Thomson's laboratory. And he went to see Thomson, and Thomson was completely uninterested. But when Bohr went to visit Rutherford's lab, it was very exciting. And he stayed there several months. And then in 1914 to 1916, he returned, and he worked out what we call the Bohr theory of the atom. So he really combined two impossibilities into one. He took Rutherford's model of the atom, and he took Planck's quantization of the black body radiation, and he, if you wish, discovered stationary states. And these, of course, couldn't exist, according to classical theory. Heisenberg and Schrödinger, but I mention Heisenberg here especially, found a way of formulating a new set of laws of physics which incorporated all of this information. But I mention Heisenberg because not only did he have a law, but he had a method. So he said if you wanted to study physical phenomena, you should only work with observables. In those days, it was the spectral lines. And if you work with observables, you just don't run into the kind of problems that people had. And in 1943 and 1944, he published a series of 3 papers where he modernized this point of view. That is, what one would study in those days, or at that time, I should say, was not so much the spectral lines, but the scattering of one particle off of another, and he formulated what is called the S-matrix theory. Now, my exposure to nuclear physics, high-energy physics at the time, came when I was 10 years old, 1947. I used to listen to the radio when I came home from school. I listened to a program called The Lone Ranger, and the sponsor was a Kix breakfast cereal. And here, I was told by the announcer that I could get one of these atomic bomb rings. All I would have to do is mail in 15 cents and a box top from Kix cereal, and by return mail, I would receive one of these, and they were true to their word. They sent me one of these. And if you took it into a closet, closed the door, and waited a couple of minutes so that your eyes would get acclimated to the light, and you pop off the top here, as you see here, and you look in the ring, you would see incredibly brilliant flashes of radiation. There was a radioactive polonium source in there. And there was a zinc sulfide screen, which is the same kind of screen that was used by Geiger and Marsden. So you could really see it for yourself. Now, a couple of years later, unbeknownst to me, of course, there was a paper in the Physical Review by Fermi and Yang, and it's titled Armazons Elementary Particles. And now let me read the abstract and a little bit from the paper. They say the hypothesis that pi mesons may be composite particles formed by the association of a nucleon with an antinucleon is discussed. From an extremely crude discussion of the model, it appears that such a meson would have, in most respects, properties similar to those of the meson of the Yukawa theory. And here they give a reason for thinking about this kind of problem. They say, in recent years, several new particles have been discovered which are currently assumed to be elementary, that is, essentially structureless. The probability that all such particles should be really elementary becomes less and less as their number increases. But they note that there's a problem right here. They say, unfortunately, we have not succeeded in working out a satisfactory, relativistically invariant theory of nucleons among which such attractive forces act. And in fact, this inability to create mesons dynamically would haunt physics later on, the people that were the practicers of the S-matrix philosophy, philosophy and the bootstrap hypothesis, which we'll talk about a little later. Now, in 1957, when I was, between my second and third year in college, in the summer of 1937, I happened to come across a Scientific American article written by Murray Gell-Mann and one of their editors, Rosenbaum, called Elementary Particles. And later on, I found out that Murray had taken an article that he wrote with Art Rosenfeld, which was published in the Annual Review of Nuclear Science in the same way, in the same year, and rewritten it for the public in the Scientific American. And it's interesting because it shows you what the state of particle physics was in 1957. There were two kinds of elementary particles. There were the point particles, and you see them up here. There were 3 leptons and a photon. And then there were a number of extended particles, strongly interacting particles. There were 2 classes, the spin-half baryons and the spin-0 mesons, and there were 7 of each. Altogether, I think there were 19 elementary particles. That seems like an awful lot of elementary particles. But the thing that was amazing, that there were no resonances mentioned. And in the very same issue of Annual Review of Nuclear Sciences, there was a review article by Sam Lindenbaum studying pi plus, pi minus p, showing you the total cross sections and where you can see the various resonances. So side by side, elementary particles and resonances, no connection. Well, after graduating from Ann Arbor, the University of Michigan in math, I decided to switch to physics and go to Caltech. I wanted to be a theorist, and after my first year at Caltech, I went to talk to my quantum mechanics professor, Bob Christie, and I asked him if I could work on some problem over the summer. And he looked at me in a really contemptuous way, and he said, "You know nothing." And then he says, "Why don't you go over to the synchrotron and learn experimental physics?" He says, "If you do become a theorist, you'll never be able to learn about experimental physics. You'll be too busy." So I didn't really have that much choice, and so I took his advice and went over to the synchrotron. And there I met Alvin Tallestrup, who was a young faculty member, and he was going to do the first users group experiment away from Caltech. So in those days, you'd have a university with an accelerator, and that's where you would do your experiments, at the accelerator located at your university. But Alvin was going to study K plus goes to pi plus pi 0 plus gamma. K goes to 2 pi plus gamma. And I thought I could piggyback off of his experiment and study K mu 3 decay, this reaction here. And the reason that's interesting is that if you can measure the polarization of the mu out of the plane of decay and it had a non-zero value, then you could show the time reversal symmetry doesn't work. That was before Fitch and Cronin found that time reversal symmetry was violated. This was like in 1959. So I worked on it for a couple of years, very, very hard, and we ran at the Bevatron. We had 21 half days. It was a rough time, but we finished, and I came home with several 100,000 pictures, and I started to look at the pictures, and I saw no effect. And this was depressing because, you know, parity violation had just been discovered a few years earlier, and it was a big effect, and here there was nothing. So this was kind of a crisis. I mean, I was looking forward to maybe 2 years at least of making very careful measurements so that I could get an upper limit that was accurate with error bars or do something else. So I just practiced denial and went to Mexico for the summer, down to the Yucatan Peninsula, and thought it over. And when I came back, I decided I would try to do theory. And I had taken theory courses, so I was prepared. I just hadn't written a thesis. So I needed a thesis advisor, and the natural choice was Murray Gell-Mann. He had many, many students. And the best part of it was that all of his students graduated quickly. So I went in to see Murray, and I had talked to him on a few occasions about a dynamical mechanism for suppressing strangest changing decays. So he was the natural choice. When I went in to see him, there was like a long silence, and he looked up and he said, no, he's not going to be my thesis advisor. And then he said that he was going to go to the East Coast, and so he wouldn't be at Caltech, but I should go. Oh, and then he said, but I'll talk to Dick. Dick was Richard Feynman. Now, nobody went in to ask Richard Feynman to, you know, supervise them in their thesis. So in any case, I was a little worried. I was anxious, I would say is the way to say it. I was anxious, but about a week later, I went in to see Feynman, and Feynman looks at me and he says, Murray says you're okay, so you must be okay. And then he tells me every Thursday, come in at 1:30, and from 1:30 until 4:15, we'll talk about physics, then we'll adjourn for the tea, and go down to the colloquium at 4:45. And in fact, that's what we did for the academic year in 1962 and 1963. Every Thursday. And before every Thursday, I'd work like crazy to try to prepare something to talk about that might be of interest to him, because I didn't want to bore him. Well, we talked about basically all of theoretical physics. There was axiomatic field theory, which was practiced at Princeton, and he hated it. There was theory that I say was related to belief. It was really sold by a man called Geoffrey Chew, and I read from something that he said in 1961. He says, I believe the conventional association of fields with strongly interacting particles to be empty. Field theory, like an old soldier, is destined not to die, but just fade away. And in fact, what's happened is that Geoffrey Chew has faded away. Okay. There was also theory related to experiment. So we talked about particle classification. Yuval Ne'eman and Murray Gell-Mann had proposed SU3 symmetry. This was very interesting, but there was no dynamics. No dynamics. But then if you wanted dynamics, then you had to go back to the extension of Heisenberg's work with S-matrix symmetry, and that was the bootstrap. And the bootstrap was really a very beautiful idea. It, at least initially, didn't have anything to do with classification, but I want to show you an example here, a beautiful example that was published in 1961 by Fred Zachariasen, who was also at Caltech. So the idea, so what you're trying to do is show that Particles make themselves. That's why it's called the bootstrap. And what that means more precisely is the following. Suppose that you scatter two pies off of one another, and you have a field associated with that scattering. And you call that field, that particle, the rho meson, a spin 1 minus resonance. You find that that creates an attractive force. Now, if that force is attractive enough, these two pions will actually bind and form a resonance. They'll form the rho. So if you insist that the properties of this particle that's being exchanged is the same as this particle which you're forming, then you can actually determine what the properties of this particle are. And he does that in that paper, and he gets answers that are roughly right. There are some numerical errors in this paper, but it's basically correct. So this was, in fact, a very beautiful idea. But the problem was, and they didn't talk about it, is that if you try to, for example, bootstrap the pi using a nucleon and an antinucleon, a little bit like what Fermi and Yang tried to do, you couldn't do it. Well, we also talked about experimental physics. And by that time, in 1962, they had found the fourth lepton, and they found the eighth spin 0 meson. In fact, they found a lot of resonances, the rho, the omega, the K star, and the precursor to the particle data group compilation, the definitive compilation of resonances, was published in the Reviews of Modern Physics in March of 1963, and there were 26 meson resonances that were listed. Well, one Thursday afternoon was particularly interesting. I was very excited. I went in to see Feynman, and I told him about this experiment that had just been published in the Phys Rev Letters. It was called The Existence and Properties of the, of the Phi meson. So the reaction was K minus P goes to lambda plus K plus K bar. This could be K plus, K minus, or K0, K0 bar. You see here the Dalitz plot for that reaction and the projection of the Dalitz plot on the KK bar axis. This is the invariant mass squared of the KK bar system. And you see this incredible number of points, and it's amazing because it's also close to phase space, and you'd think there'd be a little suppression close to phase space. So phi goes to KK bar. Now, the fact that you just had another resonance didn't really mean much. I mean, you had 26 in the particle data group. So that wasn't what was interesting. What was interesting was what the particle didn't do. So here we see the invariant mass square. Oops, excuse me. What we see here is the invariant mass square of the 3 pi system, which you would get from, for example, a rho and a pi. And there's really no large enhancement. There's nothing statistically significant. You know, maybe there's something here, but it's all in statistics. So the phi didn't go to rho pi, at least not very strongly. And if you made an order of magnitude calculation of what you'd expect the branching ratio to be, you would find that it's about 1/4. You get 4 times as many rho pi's as KK bars. You saw the graphs. There wasn't 4 times as many rho pi's as KK bars. So what was observed is that this ratio is actually 35. Now, the fact that this is a little peculiar was noted by the authors of the paper. This came out of Brookhaven. They say the observed rate for phi goes to rho pi is lower than predicted values by 1 order of magnitude. However, the above amounts are uncertain by at least this amount, so that this discrepancy need not be disconcerting. Well, they did the order of magnitude calculation wrong, or at least I don't quite know. In any case, they got the wrong number. It's 2 orders of magnitude. And I thought that the discrepancy was enormously disconcerting. Now, Feynman thought the experiment was wrong. I mean, you know, and he told me about how when he proposed the V minus A theory, all the experiments were against him, and you just forget about the experimenters. The experiment is wrong. But I couldn't do that. You see, if you're smart like Feynman, you can forget about the experiments. If you're like me, that's what you hold on to. So I had to hold on to it. And it was driving me crazy, because I had learned from Feynman that in strong interaction physics, everything that possibly can happen does in the maximum strength allowed by unitarity. And so if you have a suppression, there has to be a symmetry, but there is no symmetry. And that means that it's a dynamical phenomenon. It's something absolutely new and peculiar. So the only way I could resolve the problem was to go back to Fermi and Yang, and also to Cicada, who extended the Fermi-Yang model and added a lambda together to the proton and neutron, out of which you're supposed to make everything, and tried to modify it. Now, the problem with that model was that it didn't give you an octet of baryons. By that time, you knew there were 8 baryons in groups, and that model was surely wrong. So it was necessary to somehow take that model, but then change it in the right way. So what I did was I assumed that that hadrons had constituents, and I called them aces for reasons we'll see in a moment. There was an isotopic spin doublet, P0 and N0, and another one, lambda 0, which was heavier than the other two, and that's why I made the symbol larger. Now, if you were to assign the right composition to the vector mesons and the pseudoscalar mesons, and if you were to say that in a particle decay, the constituents in the initial state must go to the final state, that is, these aces can't eat each other, then you could explain what was seen. I called these objects deuces. And this comes from the CERN Report in 1964. So in modern notation, you had an ace-anti-ace pair, and then as they separated, they would polarize the vacuum. And out of that vacuum would pop an ace-anti-ace pair, and it would match up with the initial aces and anti-aces, and the decay would proceed this way. And since the phi had lambda and lambda 0 bar in it, and since the rho and the pi didn't have any lambda zeros at all, you couldn't get this decay. So with this rule, you got the result that phi doesn't go to rho pi. Now, the real problem was, what do you do about the baryons? Because by that time, we knew that baryons came in groups of 8 because of the SU3 symmetry. They're forming representations of that symmetry. And the only way I could get that was to say that these 3 aces would have baryon number 1/3, because if you use 3 of them, then you would get these representations like 1, 8s, and 10s, and the 8s had been seen, and I thought they'd seen a 1, and it was probably true that they had seen a 10. I mean, they had seen, I think, all of the 10 except for the omega minus. Now, there was this formula, the Gell-Mann-Nishijima formula that you see here, that allows you to compute the charge of these objects. And when you do that, you get fractional charge. Okay, so more specifically, hadrons had point constituents, and there was a correspondence between the point constituents, the leptons, I shouldn't say constituents, the point objects that we knew about that you saw in an earlier view graph, and the aces. I only needed 3 aces, but we had 4 leptons. So I thought, well, they're probably going to see another one. And so I called them aces, because you got 4 aces in a deck of cards. Now I know that I should have called them dice. But in any case, I didn't actually know how many there were. There was an unknown number, and I represented them through a set of regular polygons of increasing size. This point of view gave you an origin for SU3 symmetry, but it went way beyond SU3 symmetry. It restricted the representations in their quantum numbers. And I'm not going to go through all the details, but I just want you to note that there are lots of predictions. And it also said that certain states don't exist. So we had not only mesons and baryons without, aces and anti-aces or three aces with no angular momentum, we also gave them angular momentum. And for any angular momentum, there were certain spin parity combinations that didn't exist, and they're listed here. So there was a lot of experimental content to this idea. The symmetries were broken just by mass splittings. That was it, just the mass splittings. So SU3 symmetry was broken by making this mass larger than the other two, and SU2 symmetry was broken by making the mass of the N0 greater than the mass of the P0. And just to give you an idea of the graphical representation, we have here a representation of the wave functions of the particles in the baryon octet. Each of these little objects is called a tray. So let me tell you about two rules that we had. The first was that aces, not hadrons, interact. So in the strong interaction, for the strong interaction couplings, I had what later on came to be called Zweig's rule, and then which disappeared as Zweig's rule and was called the OZI rule. But the OZI rule is not this rule. This is a different rule. This says not only what's forbidden, but what's allowed. So let me give you an example. Before I do that, let me go back to the previous slide and indicate why these objects, these trays, are not symmetrical, or why these are not equilateral triangles. For the decaplet, they were equilateral, but for the baryon octet, they weren't, because you had to anti-symmetrize in two of the aces. So now, if we look over here, here's the what we're going to do is we're going to look at the pion-nucleon coupling constant. And here's the proton, and here's the neutron, and I've suppressed the subscript 0, but these are the aces. So there are two possibilities in the decay. These two aces, which have been anti-symmetrized, can go over here and be anti-symmetrized in the neutron, or they could actually split apart, and one goes here and one goes here. So there are 2 degrees of freedom. And in one case, you have F plus decoupling, and in the other case, you have F minus decoupling. So this gives you some idea of what the rules were for strong interaction couplings. For the electromagnetic and weak currents, well, you just created them out of the same aces. So this was a lot like what we now call the current quark model. And again, when a photon comes into a hadron, it doesn't interact with a hadron. It interacts with the ace constituents like this. Or when something like the neutron beta decays, it's not the neutron beta decaying, it's the N0 in the neutron that's beta decaying. Okay, the second and last rule was that the mass of a hadron was the sum of the constituent masses plus their pairwise interactions. And the mass splittings were much greater than any differences in the energy of interaction. But one of the main points was that there are no 3-body forces. So that's a pretty strong statement. And you ought to be able to get results from that strong statement. So let me show you how that works. For mesons, a mass of a deuce that was made out of an alpha ace and a beta anti-ace, it's just the sum of the masses minus the energy of interaction. For baryons, the mass of a tray was the sum of the masses of the aces. And then there were 3 different energies of interaction because you anti-symmetrized in one pair of aces, and that broke a symmetry, and so you had different possibilities. But it's important, in retrospect at least, to note that I didn't assume any potential function. This is not the naive quark model. I had no idea what the potential was. And it wasn't necessary, actually, to get most of the results you wanted to assume any potential. All you had to assume is no 3-body forces. So let me just very quickly run through this. I want to show you it in some detail because I'm going to ask you to think yourself, would you have adopted ACEs as constituents in 1964? And whether you would or not depends in part on what the body of evidence is. So there was a hierarchy of baryon mass relations depending about what you would assume concerning these energy of interactions. If you just said all the energies are the same, then you got this relation, which is roughly right, an inequality, a rough equality, and then an inequality. If you assumed an averaging relation, that's what you see over here. And now I'm saying using alpha and beta 1 and 2, meaning N0 and P0. And 3 is lambda 0. So if you assume this averaging relation, you get the Galmano-Kubo mass formula. The numbers that you see down here are the masses or the numbers that you would get at the time from the known masses. You also had a hierarchy of meson relations, and I'll just show you the results for the 1 minus non-net. If all the energies are the same, energies of interaction between the aces and the anti-aces, then you got that the rho and the omega had the same mass, and the k star mass was between this mass and the phi mass, and that worked pretty well. If you assumed an averaging relation for the potential, then you got this answer, that the mass squared of the phi is twice the mass squared of the k star minus the mass squared of the rho, and that also worked very well. For SU3 symmetry breaking, you said really that the mass of the N0 was greater than the mass of the P0. That's it. And then you got all sorts of relations. I mean, the simplest ones to remember is that the more negative the particle in a multiplet, the heavier it is. And that seems to be always true. But let me just call to your attention this relation here, which is my favorite one. You don't have to say anything about the relationship between the energies of interaction of the aces. All you have to say is there's no three-body forces. And if you say that, assume that, then you can relate the three mass splittings that you find in the octet. You've got a mass splitting for the nucleons, you've got a mass splitting for the xi's, and a mass splitting for the sigmas. And the relation is that if you sum these two small mass splittings, you will get the big one. And these are the numbers that were known at the time. These are the numbers that we know today. This is 8.14 MeV. And if you take the difference of what we know today, this is the difference. So it's essentially 0.2 MeV out of 8 MeV. It's good to 2.5%. That's unbelievable. So this is actually a challenge for you people that are doing lattice gauge calculations or computing masses. You ought to be able to compute this. I mean, this is a terribly nonlinear system. But unlike turbulence in water, there's sort of light at the end of the tunnel. There's some simplicity, and there's got to be some way of restructuring your calculation so that you get the relations that you've been seeing here. Okay, finally, let me just tell you, not in detail, what the relations are, but just how you can classify them. There are additional relations for the pseudoscalar meson octet and the baryon decaplet. There were orbital excitations between the quarks and the anti-quarks for different angular momentum with L.S couplings. And there were cross-multiplet relations. So for example, you could relate mass splittings in the decaplet, baryon decaplet, to the octet, or pseudoscalar mesons to the vector mesons. I mean, the relations really worked remarkably well. And the CERN report, the second one in February of 1964, had like 80 pages of explanations and relations. Well, all of this is not as easy as it looks, if it looks easy. And it does look easy. It looks very simple. I mentioned that there were 26 mesons that were known at the time in 1963. We now know out of those 26, 19 don't exist. Okay? I mean, Feynman, there was something to Feynman saying, forget the experiments. You just, but in any case, in addition, out of those 19 that didn't exist, 7 were exotic. So So you might ask, well, given that, how is it that it was possible to figure out what to do and what to assign where and so on? And this is where the advice that I got came in very handy. That is, I had spent these 2 years before studying experimental physics, and I learned what it meant to make a measurement, what it meant to measure an error, and I was able to, you know, look at the papers. There were only something like between 200 or 300 papers, read them all, and decide which ones looked reasonable and which ones didn't. We had speakers that would come through Caltech and give talks, and I had a chance to talk to them and form some opinion as to whether I thought they were really careful and serious. And putting it all together, it was possible to ferret all this out, as you've seen here. Well, what did people think of all this? I had a hard time believing that ACEs weren't real. And the reason was that they had dynamics. I mean, how else are you going to understand these decays and ACEs separating and polarizing the vacuum? How else are you going to understand that these ACEs are rotating around one another with angular momentum and that there's a spin-orbit coupling? The moment the mechanism for suppression of phi decay is dynamical, it's hard to believe that the constituents that are responsible for that don't exist. It's hard to have a consistent theory that way. When I got back to Caltech from CERN, I went into Murray Gell-Mann's office to get his reaction. And I remember him sitting at his desk. He was rather pained, but he was paying attention. And I went through basically what I showed you today. And when I was through, he stopped and looked up and he said, "Oh, the concrete quark model. That's for blockheads." And it's a wonderful, I mean, you saw the pictures of the baryons, the trays. You saw, remember, all these little blocks? So it's a sort of a multiple play on words. And Murray was very good with words. Murray just didn't believe in concrete quarks. It was deep. Even in 1972, this is 5 years after the deep inelastic scattering experiment showed that you had point constituents inside of hadrons, Murray delivered these lectures, very elegant. They were published. The article is called Quarks, and I'd like to read from that paper. In these lectures, I want to speak about at least two interpretations of the concept of quarks for hadrons and the possible relations between them. First, I want to talk about quarks as constituent quarks. These were used especially by G. Zweig. Now, there's a more precise and economical way of putting this. He could have said, these were introduced by G. Zweig. But let me go on. The whole idea is that hadrons act as if they are made up of quarks, but the quarks do not have to be real. Now, that's not my idea, but that's what we have here. And then he goes on to really say what his idea is. He says there is a second use of quarks as so-called current quarks, which is quite different from their use as constituent quarks. If quarks are only fictitious, there are certain defects and virtues. The main defect would be that we never experimentally discover real ones, and thus we'll never have a quarkonics industry. The virtue is that then there are no basic constituents for hadrons. Hadrons act as if they were made up of quarks, but no quarks exist. And therefore, there is no reason for a distinction between the quark and the bootstrap picture. They can be just two different descriptions of the same system, like wave mechanics and matrix mechanics. I think that was Murray's vision. Okay. Well, what did Richard Feynman think? Well, the part of the ACE paper that dealt with currents he had no problem with. That was just like current quarks. But he was very, very, very negative about concrete quarks. He believed, and I quote here, "The correct theory should not allow you to say which particles are elementary." I mean, that's what he believed. And what he really hated was Zweig's rule. And the reason was that he knew that unitarity mixes all channels of the same quantum number. And rho pi and k bar have the same quantum number. And so this business about phi doesn't go to rho pi just doesn't make any sense. Again, the experiments have to be wrong. Well, something like 4 years went by. I remember it was the late spring. It was May of 1968. And I was walking to the cafeteria at Caltech, and I bumped into Feynman. And he was very excited. He had just finished teaching a course in elementary particle physics, and he told me about all the subjects that he covered. And at one point, he stopped, and he turned around, and he looked at me, he says, "Have I missed anything, Zweig?" And then for the nth time, I told him about ACEs. And this time, he listened. You know, he really looked at me, and he focused, and when I finished, he said, "I'll look into it." So he looked into it. He looked at photo production data. And he worked with 2 graduate students, Finn Ravindal and Mark Kisslinger. And I remember 3 years later, I had switched to neurobiology by then. But I went back to the physics department for some reason, and I'm walking down the corridor. The other end of the corridor, I see Feynman. He sees me, and he breaks into this enormous grin. And he has, you know, occasionally this funny way of walking where he splays his fingers like this, and he smiles, and he walks right up to me, and he says, "Congratulations, Zweig, you got it right." Now, there were real serious problems that ACEs had. I think the biggest significant problem was that ACEs violated the spin statistics theorem. You had more than one particle in a state. So this was a lot like Rutherford's atom or Bohr's orbit. You can't have them. But that doesn't mean that Rutherford, you know, didn't find the nucleus, or that Bohr didn't correctly find stationary states. It means that you don't have a complete theory and that somehow things have to take care of themselves eventually. It was also like Wegener's theory of continental drift. There was no mechanism for driving continents apart. But that doesn't mean that the idea of continental drift was wrong. In fact, it was right. But I would say psychologically, there were problems because ACEs violated the current dogma. They violated the dogma of nuclear democracy, and one wasn't working with observables. Where the hell are the ACEs? You're talking about some things inside of here. It sounds an awful lot like what Rutherford was doing with the atom, and look at the trouble that that got him into. So this was a little bit like Copernicus's view of the solar system. Well, I tried to work out a way of thinking about whether or not you should accept some theory if it's presented to you, and in particular ACEs in 1964. So I think Bayes' theorem gives you an idea at least about what you're supposed to be thinking about. What we really would like to know is what the probability that ACEs are constituents is correct given the experiments. That's what we want. We want to judge that theory. And we want to use Bayes' theorem to provide some insight about what we're supposed to be thinking about. Well, the a priori probability that ACEs are constituents of hadrons, if you had no experimental information, you just think about that in the abstract, that's a lot less than 1. And the probability that you could explain the experiments if ACEs were constituents, that's close to 1. I mean, you saw that it's close to 1. So in terms of these two quantities, this thing that you want really depends upon this ratio. What is this? It's the probability that you could explain the experiments if you didn't have aces. The bar means you don't have aces, divided by the a priori probability that aces exist. And so you'll accept the theory if you can't imagine how you could get the experiments without it. If that small probability, if this thing is a lot less than the prior probability that the theory is true, then you'll accept it. And by and large, the theorists that were working in the Einstein tradition had the inequality going one way, and they didn't think that this idea of real aces was right. And the people in the Bohr-Rutherford tradition would be more inclined to believe that there was something to it. Well, when did acceptance come? How many people here know who Linus Pauling? How many people don't know who Linus Pauling was? Okay, a couple. Well, Linus Pauling was a chemist, the first chemist really to look at quantum mechanics in 1928 and apply it to chemistry. He was a brilliant theorist. He was the best phenomenologist I've ever seen. And he got 2 Nobel Prizes. And I received a letter from him just a few months after the CERN preprint came out. These were galley proofs of a book that he had written called College Chemistry. And in this book, he outlines the theory of aces. I mean, it's in there in College Chemistry. And he says, did I get it right? And yeah, he got it right. And in fact, it went into production. And I just recently went and looked at the book reviews that college chemistry book got in 1964, like in October, November of 1964. It was favorably reviewed, but the reviewer was a little confused about why Pauling was talking about aces. He thought he was going back too far, too fundamental. Well, Dalitz didn't really have any trouble with aces because he was a nuclear physicist and he just substituted one constituent for another. Feynman accepted aces only if he could discover them for himself, which is what he did in photo production. For most people, acceptance came either with the deep and elastic scattering experiments or with the discovery of the psi and the J particle, which were very narrow. And that was exactly the same thing as the phi. It was just déjà vu all over again, as Yogi Berra would say. Well, I was at the Santa Fe Institute last year, and Murray Gell-Mann was in the audience. Jeffrey West was introducing the speaker, Chris Llewellyn-Smith. And in the introduction, he mentioned that Murray and I were in the audience and that we invented quarks, and they were discovered a few years later at SLAC. And I interrupted Jeffrey and I said, no, they were confirmed at SLAC. And after it was all over, I started wondering about invention or discovery. And I came to the conclusion that current quarks were invented, and really in the tradition of Einstein, whereas concrete quarks, that is the aces, were discovered in the tradition of Rutherford and Bohr. I'd like to end by reading you a little bit from the very end of the CERN report in February of 1964. So it says here, there are, however, many unanswered questions. Are aces particles? If so, what are their interactions? Do aces bind to form only deuces and treys? What is the particle or particles that is responsible for binding the aces? Why must one work with masses for baryons and mass squares for mesons? And more generally, why does so simple a model yield such a good approximation to nature? And then after listing dutifully all the various possible interpretations of what was in the paper concludes with this line. There is also the outside chance that the model is a closer approximation to nature than we may think, and that fractionally charged aces abound within us. Thank you.
Thank you very much. Other questions?
Daniel.
To ask you, what is, it's clear, the difference is clear, but the relation between the aces and the Sakata model which preceded, which is Baryon number 1, and could anything be calculated from the proto-neutron lambda Sakata model compared to what you
No, the problem with the Sakata model, well, there were two problems. One, in the Sakata model, you made a pion out of a nucleon and an antinucleon. That's
a la Fermi.
That's right, and that doesn't work. So you can't do, you're stopped at square one. That's a problem with the dynamics. There's another problem which arises, but it has to do with the classification. In the Sakata model, if you wanted to know what the lowest mass baryons are, you would take one of the Sakata objects, and then you would combine it with a Sakata and an anti-Sakata object. And you don't then get baryons grouped in SU3 representations. So you get that wrong also.
But it must have influenced you nonetheless, because it
well, that's why
that's
why I mentioned it.
Yeah.
I mean, Fermi and Yang influenced me, and Sakata influenced me.
Sakata, yeah. If I can ask another question.
Sure.
You didn't mention the omega minus. Were you able with your aces to, as in the decaplet, you expected with
yes.
this equal spacing, but you did not mention in your talk.
Well, I didn't show you all the, yes, it gives you the equal.
You expected it.
You get equal spacing, but the omega minus is exactly the particle that is one when you construct it out of aces, you're violating the spin statistics there.
But yeah, the delta plus plus also.
Yes. So,
so
but that's right. You get the split. Not only that, you get electromagnetic splittings. It works. I just didn't outline everything.
Okay. Thank you.
Other question? Yes.
I have a comment and a question. The comment is that a colleague of yours, when you were at CERN, Feynman, wrote a very obscure paper before yours.
Wait, who was this?
Feynman.
Petterman? Fetterman. Okay, I don't know him.
He invented the randomization group, for instance.
Yeah?
He was the first one to compute G minus 2 before Fokker. You ought to have. You don't remember him, but you know him. Anyway, he wrote this obscure paper in which he concluded that fractional charges for a sequence of patterns were inescapable. I've tried today to go to the library and find the paper, but since we invented the web here, we have the worst website anywhere, and I couldn't find it.
Well, when did he write this paper?
I think it's 62.
Well, if you could send me a link, or give me the reference. My email address is my last name, Zweig at mit.edu. Easy to do.
Now, my question is, did you really have to wait 50 years to be allowed to give this talk at CERN?
Well, all right, I'm not going to talk too much about this, but let me just say that I was scheduled to give a talk at CERN about this subject. The title of the talk was Dealer's Choice, as a dealer with cards. Dealer's Choice, Aces or Wild. And Madame Fabergé typed up a notice for this, and it was posted. And I talked to Leon Van Hove. He had to sign off on the papers that I wrote to allow them to be sent out of CERN. And he refused to do so unless I published in a European journal. And I said I didn't want to do that. My salary was paid by another source. That source was paying CERN overhead for me. They gave him $1,200 for publication charges, and I was young and legalistic. So I just didn't think it was any of his business where I published. So he said, you just can't send a paper out of CERN. And after, I guess the next day when I went into work, I found that the notice had been removed from the blackboard or from the bulletin board. And I went in to find out what happened. And Van Hove canceled my seminar. He wouldn't let me talk. And when I went in to try to get my paper typed up so I could send it into the physical review, because they had a different format than the CERN preprint format, Madame Fabergé told me that she'd been instructed by Van Hove not to type my papers. So I couldn't get it typed. Yeah, so I never talked at CERN. This is my first talk, and I haven't been here since I left in the summer of '64. And it's very good to be back. It's an interesting place.
You can see from the question that I knew the answer.
That's always what you would want to do. Never ask a question, especially if you're a lawyer. You know, you're cross-examining a witness. Don't ask unless you know.
Yeah, other question?
No other questions?
Yes.
Can you go to the slide where you had your Bayes theorem?
When I had what?
The Bayes theorem.
The what?
The Bayes theorem.
Oh, Bayes theorem. Oh, yeah.
So,
I'd like to say some more about that, too. I'm glad you brought me back. Yes.
I mean, this more. So basically, you are using this to. I'm looking at it from the point of view of someone who is young and lives in a collaboration of 2,000 people, and has to go through politics rather than physics most of his time.
Wait, could you turn that off, and then I'll repeat the question, because I can't understand you.
So, I mean, you're using the Bayes theorem here to ask yourself why the acceptance of the full model took so much time.
No, I'm not asking why it took so much time. What I'm trying to do is find some guidance in how I should think about a particular theory that's been proposed. I mean, for example, Pauling, immediately saw it was right. I mean, he's a phenomenologist. He's a smart guy. He looked at all the evidence and he concluded it. So I would say he was in this tradition. What I was actually trying to do here was present something which I hope some of you will actually use if you're judging your own theories that are being proposed. You're an experimenter, and somebody comes along and he gives you some theoretical model. And you have to decide, am I going to spend 20 years of my life thinking about it?
Yeah, but what I was trying to say is that I think that the big problem here is that the majority of particle physicists don't think this way.
Well,
and the way the particle physicists think,
yeah.
If I come with a model and I have 10, 8, or many, you have 80 pages of prediction that fits, if they are intellectually honest to themselves, they have to accept it because it fits the likelihood at the best, at the maximum.
Yeah.
So, or we tell ourselves that we think this way to justify the fact that we didn't recognize, a lot of the community recognized very, very slowly that this was the right answer, or we should start thinking the way we say we think. So I really cannot understand how a community that thinks in terms of these are the data, this is the model that maximizes the likelihood, to not recognize that you were right. Let me say that it was a very strange situation, because if you were willing to take the time and the effort to go through all those papers, go through this 80 pages, and think about it, I think the conclusion was inescapable. But people weren't willing to do that.
Theorists don't know how to judge experiments. They are not going to be interested in thinking about what some other person is doing, and they got to spend all that time and effort. It's just the way that society, or it's just the way that a social group of physicists will behave. I'm not surprised. I think it was obvious, but only, it's what I said before, it's not as easy as it looks. But if you were willing to spend the time and you had the knowledge, then it was inescapable. I wanted to say one thing about this slide, and that is that in this day and age, there are two kinds of theories. There are theories that make predictions about experiments. And there are theories that have not yet reached that point. Theories like string theory. So if the theory is one where it's related to experiment, then I think you should use this kind of thinking. I think it's useful guidance. If you're trying to evaluate another theory like string theory, then I think this guidance is also relevant, but you have to replace what's here as the experiment, which is the ground truth, with the theory that's known to be true or believed to be true, which is a standard model. So you would ask questions like, what's the probability that string theory is true, given that we know that the standard model is right? We have some information, but it's theoretical information. And then you have to ask yourself, well, how hard would it be to get the standard model if you didn't have string theory? So I think you can still use these ideas, excuse me, but now we have this different class of theory that's actually available.